We're pleased to have a distinguished seminar speaker today. Thomas Overbye, the TEAS. TEAS stands for Texas Engineering Experiment Station, right?
It does.
Distinguished research professor. That means you don't teach anything?
I do teach.
You do, okay.
Somehow they forgot that part.
Tom Overbye is no stranger around here. He was on the faculty for 25 years. Comes from Wisconsin, Madison, all 3 degrees, plus a few years at Madison Gas and Electric to learn how the business operates. And he's a fellow of IEEE, the founder, genius, creator of Power World Corporation, and a member of the National Academy of Engineering. So I'm pleased to bring and welcome Tom back.
Thanks, Pete. Oh, I guess I'll open it later. Thanks, Pete. It's very nice to be back here. As Pete said, I spent 25 years on the faculty here. Actually, my kids are still up here, 2 of them in town. One just graduated in mechanical engineering from Illinois, and then my daughter is a junior here as well. I'm going to talk about enhancing the resilience of large-scale electric grids, something that I'm very interested in. So I think everyone here knows that we depend on electricity. If the lights went out, we probably wouldn't be doing this seminar for very long. Right now, about 40% of the energy we use is transmitted in the form of electricity. So if the lights go out, if we have a blackout, the cost can be quite high very quickly. It's hard to know exactly how much blackouts cost, but some people say they can be up to $100 billion a year. And that's just the normal blackouts that we have kind of regularly. What we're really concerned about are the catastrophic blackouts that could occur. And this talk is focusing on how do we reduce the risk of those events? What sort of events are they? The picture on the bottom right there is actually from the August 14th, 2003 blackout that affected the east coast of the US and Canada, that blacked out 50 million people. The magazine or the newspaper cover there is showing the people streaming out of New York City as a result of the blackout. The picture on the top is wind turbines from somewhere in Illinois, I believe. And one thing about the grid is most of our renewables are ultimately converted into electricity. So electrification plays a big role in renewables as well. So in doing this talk on resiliency, I do have to differentiate it a little bit from reliability. The goal with the grid is to keep the lights on, and that does involve 2 related concepts, but subtly different as well, and that's reliability and resiliency. If you look at the definition, reliability, it's suitable or fit to be relied on, dependable, and it's certainly one of the key benefits of electric grids. Resiliency is the ability to recover from or adjust easily to misfortune. And as I was trying to think of something that is reliable but not really resilient, I was thinking about windows. And if you think about a window, usually it's pretty reliable. It keeps the rain out. But if you hit it with a strong enough blow, it's going to break. So it's reliable but not particularly resilient. The power grid has had resiliency for a long time. If you think about, probably most of you don't know about transmission lines in terms of how they respond to lightning strike, but when lightning strikes a high voltage transmission line, our goal isn't to keep that line energized. In fact, our goal is to quickly de-energize the line, take it out of service, so the line in and of itself becomes less reliable, I suppose. But the protection system opens the circuit breakers, takes the line out of service, and then within a couple seconds usually puts it back in service. So it is very resilient. It bounces back from that lightning strike usually very quickly. And you see this during a thunderstorm when the lights blink. That's resiliency in action. One issue that we've been looking at the National Academies is the idea of making the grid more resilient. I was able to participate in 2 recent National Academy studies. In fact, our department head here, Bill Sanders, also participated in one of them on enhancing the resiliency of the nation's electric grid. And I did want to read a quote from that report, and that's shown in the middle there. And it says, while minimizing the likelihood of large area, long-duration outages is important, a resilient system is one that acknowledges that such outages can occur, prepares to deal with them, minimizes their impact when they occur, is able to restore service quickly, and draws lessons from the experience to improve the performance in the future. That's the focus on what we're about here and what that report was about. Both of those reports are available online. If you're interested in getting them, the easiest way is to just Google the title of the report. Maybe you stick in National Academies, and you'll easily be able to download the PDF for them. So what are some of the things that we're concerned about with respect to the electric grid? This is a figure that I grabbed from the 2017 report that I just mentioned. What it does is it tries to break up some of the big issues that we're concerned about in terms of how much warning time would we have before the event, and how much time would it take to restore service after the event. What it doesn't show is how large the event could be. So on the top right, where we'd have a lot of warning time, but it might take a long time to restore service, is a drought or an associated water shortage. Usually you're not struck by a sudden drought. At the bottom left, an earthquake is something where you could get very little warning time on that earthquake. And depending on the magnitude of the earthquake, you might be restoring service quickly, or you might be restoring service in days to potentially weeks or longer. One of the longest events there is a volcanic eruption. We'd probably get some warning time, but if it was a big volcanic eruption, it might take out service for a long time. So hurricanes are in there. So different events that we're concerned about. The ones that I'm focusing on primarily are the major events, and I'll talk about those in just a second. Before doing that, I did want to give just a quick cartoon view of the electric grid, recognizing that this is a more general seminar. The electric grid, what we're doing is we're creating electricity. That is, we're generating it. That can come from a traditional power plant like a natural gas or coal plant. It could come from hydro, it could come from nuclear, it could come from a wind turbine. We usually step it up to a higher voltage, send it through what's called the transmission system. That operates at voltages up to 765,000 volts. Then we take it and distribute it to the lower voltage, what we call the distribution system, and then ultimately on to the load. The distribution system, the lower voltage system, is the source of most outages, but these are almost always small-scale events. Okay. If you know Professor Sauer, you know what he thinks of as the major cause of blackouts, which is right. That's the real cause of most blackouts is squirrels. If you're interested in how tough a squirrel can be, talk to Professor Sauer. I lived out in the country, and one time our power went out. This is out by Homer Lake. And the utility guy comes out, and they go back, and they find a now-deceased squirrel. They bring the squirrel back. For whatever reason, they showed it to my wife. She verified that it was a now-deceased squirrel. Then like a couple hours later, the power goes out again. They come back out, and they find the squirrel's friend has also met his demise. So squirrels cause a lot of outages, but they're usually very small ones on the distribution system. Sometimes it's the trees. This is a beautiful lake in southern Indiana. These were actually trees that caused an outage on August 14, 2003. That was when the big blackout occurred that took out the Eastern Interconnect. However, these trees caused an outage on a 345, 230 kV line, but they weren't the ones that caused the big outage. They just caused a little outage in Indiana. Turned out that the utility was actually trying to trim those trees beforehand, but the property owner was objecting to that, so they weren't able to trim them. It did cause an outage. After the August 14, 2003 big event that took out 50 million people, nobody was too interested in having trees take out high voltage transmission lines. So it took about 2 months, and the utility finally was able to trim the trees. That's the after trimming picture. And I was over there talking to the utility involved as part of the August 14, 2003 blackout. I said, yeah, you guys really did trim those trees, didn't you? They said, yep, we trimmed them down to 6 inches. So they're not trimmed to the ground. They left a little bit of the tree there. You can see the remnant in the front there. But trees can cause outages, and actually the August 14, 2003 blackout was ultimately caused by 3 trees, or three events were caused by trees in Ohio. What we're talking about here is what we call high impact, low frequency events. These are events that, if they were to occur, they could cause almost unthinkable impacts on the electric grid. Now, luckily, they're low frequency. Some of them have never occurred. What would be an example of one of these events? Well, a coordinated cyber-physical attack on the grid could cause quite a bit of damage to the grid. Geomagnetic disturbances, which are something that we're going to talk about a little bit later on in the talk, their potential to cause havoc with the grid. High altitude electromagnetic pulses are one. Another one is pandemics. Pandemic isn't because the grid gets sick, it's because the people that operate the grid might get sick, or they might get too scared to come into work, so you could have a long duration outage. The figure there says, as a result of one of these events, we might have to operate the grid with substantially less capability for a long period of time, and that period of time could go out to days, to weeks, to months, to potentially years. Okay. Before we get into considering those, I did want people to understand that the electric grid is a large interconnected system. In North America, we've got 4 major interconnects. Here in Illinois, we're in the Eastern Interconnect. The Eastern Interconnect covers all the way up from provinces in Canada all the way down to Florida. It actually comes all the way into where I live in Texas, Brazos County. Part of where I live in Texas is in the Eastern Interconnect. The second biggest grid is the green one. That's the Western Interconnect. It covers Canada, most of the western US, and then a little bit of Mexico. Quebec is French-speaking, so they've got their own French-speaking grid up there. And then in Texas, we like to be independent, so we've got our own grid that covers most of Texas. It's called the Electric Reliability Council of Texas, or ERCOT. But Texas is actually, part of it's in the east, part of it's in the west, and most of it is in ERCOT. Okay, so when we're operating the grid, we have to deal with a lot of different time frames. The best graphic that I've ever seen on the electric grid time frames comes from Professor Sauer's book, and it shows on the bottom axis there time frames ranging from less than microseconds out to weeks, and it could be extended out to months and years. On the short time frame, we have to deal with lightning propagation, where very quickly you have a lightning strike on the grid. That electromagnetic pulse can move through the grid at nearly the speed of light. You can get switching surges. They can interact with inverter-based controls. And then you get progressively slower responses on the grid, going through dynamics associated with, say, the boilers on the generators and their governor controllers, all the way out to determining which generators we turn on, something that we call unit commitment, out to decisions that take months and years associated with planning the grid. In operating the grid, we do have to take into account some special considerations. One of those is that electricity cannot be economically stored. What I like to tell people is when you plug in your toaster or your computer, because we can't store electricity, you're guaranteed you're getting fresh electricity. It was generated just milliseconds before it was used, so it's always fresh. But to accomplish this, the generation has to continually be adjusted to match the electric load, to match so it's equal to the electric load and losses. Another issue of concern is electric power flows on the high voltage line cannot be directly controlled. That is, we don't have any valves that we open up and close to change how the power flow goes through the line for the most part. I mean, there are some exceptions, but mostly it's an uncontrolled, free-flowing grid. And the map on the right shows the high voltage grid. Looks like a mess, but if you're a power engineer, it's a very dear mess. The third part is the customers are in control of their load for the most part. You get to turn, or you get to decide when you turn on and off the light switch or plug in your computer. And then lastly, it's usually economical to push the transmission system to its limit. It has limits, and we're often operating by those limits because of economic reasons. Okay, so actually operating the grid in the best of times can be a challenge, and we have to operate it in both the best of times and in the worst of times. The grid's subject to lots of different disturbances. That one on the right on the top I got from one of my friends in a utility in the Pacific Northwest. They had an outage on one of their substations, 115 kV substation, took out a couple thousand customers. Turns out somebody's trampoline had blown into the substation. And that thing that you see stuck in there is a trampoline. And I've had my trampoline blow away, so it's good to anchor them down. So after seeing that, I always make sure I anchor down my trampoline. But there are other events that could cause large-scale disturbances. In the Midwest, an ice storm is a potentially catastrophic impact. We haven't had an ice storm here in central Illinois, at least not a big one, for a long time. I think the last one was like in 1990 or something. The picture there shows towers that were toppled by an ice storm in Quebec, Canada. Tornadoes, hurricanes can cause large-scale damage. In operating the system, we have to take this into account. When you operate the power grid, usually you're in the normal situation. Normal situation, we're operating the grid so that if any single device fails, we'll be okay. Then perhaps suddenly something could occur, you lose some devices, you go into alert situation. In the alert situation, you're worried about a potential failure. If that failure starts to occur, you go into emergency operation. Eventually, you might get into what's called in extremis. In extremis, you're in danger of losing a large chunk of the grid, something we saw on August 14th, 2003. If you do lose the grid, then you go to restorative, and hopefully you get back to a normal. So these are all things that need to be considered when operating the grid. In terms of how we model it on all different time frames. One way we model the grid is on what's called the quasi-steady state time frame. That's what we call the power flow. In the power flow, we're treating our power grid model as a set of coupled algebraic equations. The idea is that we're making assumptions on how fast control actions take place. Some things we assume take place so quickly in the power flow that we can treat them as constant. In the power flow, which I'm going to show you an example of in just a second, we're moving from one essentially quasi-steady state operating point to another one. To give you an example of this, if we looked at the August 14th, 2003 blackout, this graph on the left here shows different events that occurred over the time scale of that blackout. That blackout played out over the course of more than an hour. And as it played out, different discrete events occurred. Okay? It started out with some generators failing, and then it ended up with a good chunk of the grid failing. If you looked at the flow on the transmission lines, they changed in discrete amounts, and that's shown on the graph on the right. At least the assumption is they changed in discrete amounts. As each one of those events occurred, if we modeled the full dynamics, we'd see the grid oscillate a little bit. What I'm going to show you right now is a simulation of what happened on August 14, 2003, at least in the start of the event. And this is going to be a power flow simulation. So we'll go from one steady state operating point to another steady state operating point. This here is a visualization of the high voltage electric grid as it existed in Northeast Ohio in 2003. The green arrows, which you can kind of see flowing there, visualize how the real power, the megawatts, were going through the system. So if you're using, 25 watts to light a light bulb, that's 25 watts of real power. The arrows are showing power flow on the lines, except they're higher values of power, maybe several hundred megawatts or millions of watts or perhaps more than 1,000. In this case, I am not showing every transmission line here. So if you live in Pennsylvania, there is actually an electric grid there. I just didn't draw it in. But I kind of drew in the key lines that affected the power grid on August 14th. The colors there show the voltage levels of the line, at least in terms of their nominal voltage. In that part of the grid, the highest nominal voltage was 765 kV. There's just one line there. It's shown in green right here. The red lines are the 345 kV transmission lines. They were kind of the bulk of the high voltage transmission grid. Then the littler black lines were the lower voltage 138 kV lines. Okay, so this would be a steady state power flow operating point. Okay, and then kind of unexpectedly, one of the transmission lines tripped out of service. It was one that was not heavily loaded. The pie charts there, which are kind of hard to see in the back, but they're showing the percentage loading on the lines. The line that tripped out first was actually only loaded at 37% of its limit. It opened up because a tree got too close to it, so it arced. The protective relays took out the line, and then they tried to put it back in service, but because the tree was still there, they couldn't. The line went out of service. When that line went out of service, the power flow on the system instantaneously, or almost instantaneously, redistributed itself. So a couple other lines picked up the slack. What the colors in the background are showing is a contour of the voltage magnitude across the grid. Okay, when we operate the grid, we need to keep the voltage at a high enough level. Okay, for example, at the wall socket, it's 120 volts. The way power engineers express this is in terms of a normalized value. We call it per unit. This contour is just showing the normalized values. And let me put a key on there. Usually we try to operate the grid so that it's close to 1 per unit, or what its normal value would be. 138 kV lines should be operated 138 kV. It can be operated a little bit above that, 141, 142 kV. But if it goes too low in voltage, you start running into problems. Well, the issue on August 14th, 2003 was nobody knew that first line went out of service. Then a half an hour later, a second line went out of service. That was loaded at 77%. When that line went out of service, the power flow again instantaneously redistributed, but now they started to get some transmission line overloads. The line started to heat up. Okay, the people up in the Cleveland-Akron area were still using electricity, but now they have some overloaded lines. And because we lost some parts of the system, the voltage was starting to fall. Again, nobody in the control center knew that that second line had gone out of service. But some of the customers knew there was a problem, so they started calling up the utility saying there were some problems. Yes? The second one was also a tree contact. Then there was a third line that went out of service, again caused by a tree contact. And as that third line went out of service, we started to get even more lines getting heavily overloaded, and we moved into what we'd call a classical cascading blackout. Now some of the lines, protective relays, started to trip them out of service. You started to lose load, and gradually over the course of the next half an hour, the grid got more and more stressed and eventually failed in a rather catastrophic way. As we get to the part where the grid fails, you start getting dynamics going on. And the grid starts oscillating around. It's no longer in what we call a quasi-steady state condition. And this is something that we study in power system dynamics. We start talking about differential equations coupled with algebraic equations. Now we move from a modeling time frame of perhaps minutes out to dozens of minutes to a time frame of seconds to less than a second, maybe on the order of one cycle, which would be 60th of a second. What I'm going to show you in the next visualization is how a power grid would respond to the loss of generation. This is a graph showing the system frequency. Usually the frequency of the grid is around 60 hertz. When a generator fails, we lose some generation. So as you lose generation, the system starts to decelerate. It starts to slow down. As it slows down, the frequency drops. As the frequency drops, we get a protective control system responding, and ultimately devices known as governors are telling the remaining generators to up their power output, and hopefully the system stabilizes and comes back to a new equilibrium point. But that doesn't occur uniformly across the grid. It starts to oscillate around. What I'm going to show you next is a visualization of how the Western interconnect would respond to a disturbance in terms of its frequency variation. So this is going to be a movie. This movie is going to run at 1/3 real time. So you'll see how the frequency changes. I'm again going to use a contour. On the contour, when it starts out, it's going to show 60 hertz. And then you'll see colors emanating out of Arizona. Those are low frequency caused by the loss of a generator in Arizona. And you'll see how it propagates through the system. So right there, a generator in Arizona fails. The frequency disturbance moves through the system. It moves through the system at about 1,000 miles a second. It gets up into Alberta, causes low frequency in Alberta. It kind of bounces off the edge of the system and then kind of oscillates back down. Eventually, if it's a well-designed system, things should damp out and eventually recover. Okay, and in this case, it will eventually recover. Okay, and it's recovered at a lower frequency. Other control systems over the course of minutes are going to restore the frequency gradually back to 60 hertz. That's if the system isn't too stressed. If you look at what happened on August 14, 2003, in terms of the dynamics, this is showing the response of the grid right as it was breaking up. This graph shows on the order of about 30 seconds how the grid flows. In this case, it's power flows. We're responding. You're seeing the red line, you get some oscillations going on. The blue line is showing higher frequency oscillations. As these oscillations are going on, the grid's falling apart, and eventually it resulted in a large blackout. This is showing the frequency on the system over the course of those same 30 seconds. The difference here is the scale is much, much larger than the scale on the visualization that I just showed you. In the visualization I just showed you, we went from 60 hertz to about 59.9 hertz. Here the scale is 60 hertz, 61 hertz, 62 hertz, 59, 58. So there was a large disturbance on the grid that day that ultimately resulted in the blackout. Okay, what we're concerned about, though, is there can be even larger events that could impact the grid. These are what we call the high impact, low frequency events. Some people call them black sky events. One of the events that we've been studying recently are geomagnetic disturbances. These are events that would be caused by a corona mass ejection from the sun, travels from the sun to the earth at about 1 million miles an hour or 2 million miles an hour. So a day or two later, it impacts the Earth's magnetic field, causes the Earth's magnetic field to oscillate around. That oscillation induces what we call geomagnetically induced currents in the grid, or GICs. These are low frequency variations in the power grid. So as power engineers, where we're used to 60 hertz variation, anything that's below a hertz we call quasi-DC. So they look like they're almost DC. The issue with the GMD is the GMD could impact a large part of the electric grid in North America. This visualization right here shows a GMD that occurred in March 1989. This is the Earth. This part right there is North America. That crescent shape covered a good chunk of the northern part of North America. This event caused the blackout of Quebec in 1989. It turns out that the Quebec event was relatively small compared to what we've seen in the historical record. In the historical record, we've seen storms that might be 5 times as large as the Quebec event. One occurred in 1859. Another one occurred in 1921. The graph on the right shows the, what people think was the geographic extent of those events. One of the issues with trying to figure out how big a magnetic field variation occurred in 1859 is we did not have an electric grid to check it out with. Okay. But actually, we did have telegraph systems, and the reason why we even know how big the 1859 storm was because people found they could operate the telegraph system without batteries. The magnetic field causes a change, or the magnetic field is changing, that induces an electric field, and if you have an electric field over many miles, causes a voltage on your lines, and those voltages were running the telegraph system. How big these fields are depends upon a lot of different parameters. It depends upon how big the disturbance was that came off the sun. It also depends upon the deep Earth conductivity, where we have to look at the Earth conductivity going down hundreds of kilometers. So it's a challenge to assess the impact of these, but it's something that the electric utility is looking at right now. There are other events that can do similar types of damage to the grid. GMDs are naturally occurring events caused by something on the sun. Another event is a nuclear EMP. In a nuclear EMP, an explosion of a nuclear weapon at high altitude, perhaps 100 kilometers or 200 kilometers up, causes an electromagnetic pulse that impacts the grid. The electromagnetic pulse has different time scales associated with it. One part, E1, is very fast. It causes a high electric field that would fry electronics. Another one, called the E3, is relatively slow. It changes on the order of seconds to minutes. It looks like a very large geomagnetic disturbance. It's what we call the E3. The E3 could actually also cause damage to a large part of our grid. Why do we know about EMPs? Turns out when nuclear explosions were still going on in the atmosphere, people could measure how much change occurred as a result of the explosions. One in 1962 over the Pacific Ocean is called Starfish Prime. It actually blacked out, or it knocked out streetlights in Honolulu, which was about 1,000 miles distant. So these nuclear EMPs can cover a large footprint. So we're concerned. One person was talking to our National Academies Committee about EMPs, and he said, yeah, over the last several generations, different countries have spent a lot of money on optimizing nuclear weapons for EMP capabilities. So there could be quite strong EMP capabilities. How they impact the grid is these GICs, or these low-frequency currents, flow through the grid, because at low frequency, the high voltage grid looks kind of like a DC circuit. The three phases are in parallel, so it looks like three lines in parallel. So the GICs superimpose on the DC, or on the AC flows. We can calculate how these GICs flow through the grid. This is a simulation that we're doing, looking at if we put a GMD assumed scenario over the eastern interconnect. The yellow arrows show how the GICs flow through the system. You can see they're kind of correlated. We assumed an electric field going east to west, so most of the GICs are flowing east to west. So we're doing studies that look at how do these things impact the grid. One way they impact the grid is when you take a AC waveform and superimpose a DC waveform on it, you push it into nonlinearity. In a device that is using magnetic material, you actually cause saturation in the magnetic material. This introduces harmonics, and these harmonics can cause increased reactive power loss in your transformers. From an operations point of view, if a GMD were to occur, it could be a really bad day. Okay, there would be some warning time that a solar storm is coming in. You may see these in the news periodically. We do have small storms quite often. If it were a large storm, we would observe it on the sun, but we wouldn't know how bad it is. There is a satellite 1 million miles from Earth that's something called the Lagrange point. At the Lagrange point, the satellite would let us know that, hey, there's something bad that's coming in, but we still won't know how bad it is. As it actually hits the grid, suddenly in your control centers, a lot of things could change simultaneously. Reactive power loadings on hundreds of high voltage transformers could change quite quickly. Okay, so as these change, you would get heating, control center software could fail, control personnel would be overwhelmed, the storm could last for days. So what we're trying to get the message out to the utility industry, and they are getting the message, that waiting until the last moment, waiting until a storm's coming to prepare isn't a good idea. So right now, the electric utility industry is starting to do plans to determine what they would do if such a storm were to occur. There are different things you can do, but all of this has to be considered in a cost-benefit point of view. Okay, if you're an electric utility, you don't want to spend a lot of money preparing for a GMD that may never occur. So they're trying to figure out what are the best things to do. One device that could be installed is what's called a GIC blocking device. That's a picture of a GIC blocking device installed in a substation in northern Wisconsin. The GIC blocking devices block these geomagnetically induced currents from getting into the ground. When you do that, you can potentially reduce their magnitudes. There's also other operational changes that you can make. In considering this on the National Academy's report, we did go through some specific recommendations, but I won't cover them here in the interest of time. Rather, I'll focus on one of them. One of the specific recommendations was we as an electric power grid community need to have better systems that we can study. Ideally, we'd study the actual electric grid, okay, and some of us do. The problem with studying the actual electric grid is it's considered critical electricity infrastructure information, or CEII. So if I study the grid, I can't share my results with anyone else, okay, or not, I can't share my results that widely. So our solution is to create synthetic electric grids. These are fictional grids, fake grids, that mimic the complexity of the actual grid, but are, have the same properties as the grid. And when I was here at Illinois, we got a project funded by DOE through the ARPA-E program to make these synthetic grids. So we're working on the synthetic grids. Professor Sauer here is actually now in charge of that project, although we're certainly helping out at Texas A&M. So we go through and we make synthetic electric grids. We're using them in all different sorts of applications. And I'll quick show a movie here before we finish up one of those applications. This is something that we did in our undergrad lab at Texas A&M. We ran in real time a simulation, a synthetic grid that covered most of the state of Texas. And we showed to the students a tornado scenario where a tornado rapidly went through a substation here, took out 3 lines. Then as those lines go out of service, the grid starts to oscillate, and the students had to fix the problem. Okay, so these are undergrads at the conclusion of a power system analysis class, similar to what's taught here. I'll play it again quick. Most students did not solve the problem initially. But actually, they did eventually, most of them did eventually solve it. How they solved it is the little magenta fields here are showing generators where they could change the output of some generators. They could also trip load. So they got a feel for how fast power system dynamics can respond and how you can take corrective action to fix them. We've made up a 10,000 bus system covering the western US, 25,000 bus system covering the East Coast. Recently, we just created a 70,000 bus system that covers the entire US portion of the Eastern Interconnect. And we are releasing these publicly. Actually, to release them publicly, we need University of Illinois officials to sign off that they have no confidential information in them. The only reason they can sign off on that they have no confidential information is Professor Sauer tells them they have no confidential information. He knows that because I tell him that, and I know it because my grad student tells me, so it goes up the chain of command. But we can say that one has no confidential information. So what's the conclusion? The grid's critical. We're going to need it for decades into the future. A perfect grid is impossible, but we do need to be prepared for these long-term wide area blackouts. We can do a lot to reduce the risk, something that we're working on. We're trying to do this in a broad, sustained effort. My feeling is these synthetic electric grids are going to play a crucial role in this effort. And with that, I will finish up.
Okay. We have a couple minutes for some questions. I would say if you're interested in this topic, ECE 330 is the first class that touches it, followed by ECE 476, and that's in the fall, and ECE 576, which we're teaching right now. And anyone with a question? Boy, big group here. Yes.
Hi, I was wondering if you could talk about what's happened in the Caribbean with the hurricanes down there. That Puerto Rico is a case in point. Yeah, if we could see what happened there and how are they recovering.
And that's something that's near and dear to us in Texas as well, because prior to the one that hit Puerto Rico, we had Harvey come through my part of Texas. We got 20 inches of rain from Harvey and College Station, but we sent our rain south to the Houston area, so we got impacted by that in Texas as well. Not as severely as Puerto Rico. In Puerto Rico, the whole electric grid got, destroyed. It's hard to operate a grid when your whole grid gets destroyed, So if you're in a hurricane susceptible area, what are you going to do? Undergrounding transmission lines can help, but it's hard to do a whole island like that, and it's very costly to do. Puerto Rico was a complex situation because some people said the grid was in pretty bad shape to begin with. Okay, but I mean it's a challenging problem. There's not a simple answer to that.
Yes, go ahead and just talk loud.
Well, microgrids are a good solution in some areas. Microgrid is a small electric grid. Microgrids have some inherent resiliency associated with them. In a microgrid, like we could make the EC building into a microgrid, or there have been proposals to make the College of Engineering or this part of it into a microgrid. What you need to do a microgrid is you need to have generation sources, close to the load. So if we wanted to make a microgrid up here, there's been talk about putting solar on this building. There's talk about putting solar on the parking garage. You'd have to have enough additional generation to meet the load. So you'd have to put some natural gas turbines in here.
We do have diesel in the backyard here.
Diesel's useful to some extent until you run out of fuel. Uh-huh.
We did the opposite. We used to be distributed, and we interconnected because we wanted to help our neighbors, and we also have economics. We can sell cheap power to our neighbors.
I just had one of my Aggie undergrads. She sent me her senior design thesis today, where her premise is we should break grids up into, it's called adaptive islanding. When a disturbance occurs, you set the grid up to break into littler chunks so that you can save part of the grid. And that's a potential solution. The Western grid is designed already to adaptively island. It has ways to split in half so that you might have a disturbance, and rather than losing the whole thing, you only lose part of it. So that's one way to do it.
That was actually a very good comment. In fact, in 2003, they could have disconnected Cleveland, right?
Yeah.
If we had disconnected Cleveland, the blackout would not have happened.
The American electric power operators in 2003 were all set to disconnect from First Energy, but then the lines tripped out on their own and they disconnected, so they didn't have to adaptively island.
And I think the mayor of Cleveland didn't like the idea of disconnecting his city. Any other questions? These are interesting things.
Uh-huh.
Yeah.
So last time I started working at General Electric, when they started ramping up their HVDC
Uh-huh.
lines with our utility, with our transmission levels, I was wondering if your research has covered all of incorporating more HVDC lines in America. I know it's popular from Europe, and we have some Canadian lines from the East Coast coming down. But has that been a topic of research in terms of resiliency?
Yeah, the question was associated with using high voltage DC to transmit power. High voltage DC is used to transmit power, as you noted. There's a lot in Europe. We have some here in the US. The Pacific Intertie is one example where they take a lot of power from northern Oregon down to southern California. The challenge with a DC line integrating it into an AC line is you have to take the AC, rectify it into DC, transmit it, and then invert it back. So DC is a growing option, and there's a lot of interest in adding DC to the system.
But
yeah,
it is expensive too.
Well, yeah, it's expensive. We always are dealing with cost-benefit trade-offs there. I showed the grids, and you might say, how come the East and the West aren't interconnected? And that's because there wasn't much transmission out there between, you know, it's in the Great Plains where not a lot of people live, but we're now adding a lot of wind generation out there. So there are talk of either adding more DC capacity between the grids or interconnecting parts of the grid.
Any other questions?
Yes. I hadn't heard about the blackout in Brazil, so I really can't comment on the blackout in Brazil. I will say that when the August 14th, 2003 blackout occurred here in North America, there were a lot of people commenting on how the North American grid was so rickety and we should be following the lead of Europe, where Europe had this great electric grid. Well, 1 month later, Italy demonstrated that their grid wasn't quite as good as people might have thought by blacking out their country. So blackouts occur. Those of us who work in the power area know we can't totally eliminate them. There's always some event that could take out the grid, but we can reduce their likelihood. So I don't know about the Brazil event, but I can tell you in general, when a blackout occurs, you want to look and say, why did this occur, and how can we minimize that risk going forward?
Yeah, I have an old student, Henry Louis. I don't know if you remember
I
Henry.
remember Henry.
He went to Africa for a year on sabbatical leave, and he worked in cities where the electricity was only there for about 6 hours a day. And he was there to help with that situation and installing solar to help them get their electricity 24 hours a day. So there are some, not just some, there's a lot of places on the earth that electricity is not in existence 24 hours a day, with or without blackouts. Okay, we're getting near the end of the hour. Let's thank Tom Overbye again.
Thanks.